Okay, well. Okay, hello? Am I live? Is anything happening? Uh, this is all very experimental, and I don't know what's happening. Okay, well. So, if anyone is out there and viewing and can hear and see me, please shout or wave in the chat, say something. And I guess I'll start an actual sciencey talk in a few minutes. If it looks like there's some viewers, some people here. Yes, I'm live. Yes, it's working. Excellent. So this is all very experimental. Cafe Sci has not done a live stream before, and I have not done a live stream before, and we'll just see how it goes, I guess. My name is Dale Hodgson. I'm a postgraduate researcher at the University of Leeds in the School of Mathematics, working on quantum computing and quantum foundations, and that's what I'm going to be talking about a bit today. I'm not going to be assuming any knowledge of quantum mechanics or mathematics or degree level STEM or anything. It's going to be quite a light introduction. Because honestly, no one really understands quantum mechanics. It's all difficult to explain, but I'm going to give it a go. Do you have people in chat? We have viewers. Apparently, you can hear me. And yeah, it's really weird doing a talk with no actual audience in front of me. I don't know how to deal with this. There's no one to look at. There's just a camera and some lights. And it's also really weird having to keep talking all the time. It's like on radio, you can't leave dead air, and now I'm just rambling to try and fill space and not let everything go silent. Excuse me, that's just a cough. I'm not infected, luckily. I hope everyone is at home, staying safe, not going outdoors. And I'm looking forward to hearing about some science, possibly. We have now 20 viewers. My goodness, 20 viewers. It's like an actual room of people that I can't see. You're just out there somewhere. Okay, shall I talk about some science then? I suppose it's about time to start. So, what I want to talk about is a general overview of what quantum computing is, where it comes from, what the point of it is, which means explaining a little bit of quantum physics, where quantum physics differs from classical physics, a little bit of computing theory, and then kind of talk a bit about how they connect to each other. This is a rough gist of what I'm going to try and go through. Should use Zoom next time. Doing fine. I was occasionally checking the chat messages. Cafe Sci Huddersfield, yes please, good job. Organizer Rosie is not even in the same room as me, so this is all very, very strange. Computers, quantum mechanics, physical systems, security, these are all things related to my own research, but like I said, I'm going to take quite a light overview, easy introduction to them all. So the first concept I want to introduce is something called Moore's Law, which is an observation in the development of computer technology over the last century that the number of transistors you can fit on a integrated circuit of a given size doubles every couple of years. It's a really simple observation. It basically says computing power is increasing in the devices we have. In a few years' time, this phone will be twice as powerful with the same size. This kind of technological development is always going on, and is what leading to needing new physical concepts to develop newer computing technology. As things get smaller and smaller, we introduce quantum scales more and more, and then we have to deal with different physical problems to just electricity and wires. We're dealing with physical oddities in the quantum realm. And that will hopefully, in a few years' time, or maybe more, give us a whole new scale of computing power than we've ever had before. But it also introduces a lot of problems because quantum mechanics is weird and we've got to work around them. So, quantum mechanics is the physics of very, very small things, subatomic things usually. And it works a little differently to classical physics. So, in the gist of classical physics, we have these 3 points that basically sum up the whole scheme of what physics is about. We take some measurements of our environment. In this example of a gentleman kicking a football, the simplest classical physics example we can have, it's a ball moving through space. It's a trajectory. It's Newtonian mechanics. If we want to measure this scientifically, we start by measuring the ball, measuring the speed of the kick, the force that's going to be exerted on it, and we can do that to as great a precision as we would like to, usually. If we use a meter stick to take these measurements, then our precision is going to be plus or minus 50 centimeters. It's not going to be great. If you want to be more precise than that, then we pull out a tape measure or a vernier gauge or a laser measure until we can measure down to millimeter accuracy or even nanometer accuracy. And that's what gives us all of our starting data to work with. Then we follow by applying some laws and equations. In this case, like I said, it would be Newtonian mechanics, classical equations, the force of gravity downwards, air resistance, fluid mechanics if you wanted to. These are all just equations born of experiment and observation that we can then reuse to make future predictions. Our third point. If we know the starting position of a ball and how fast it's moving, we can make predictions about where it will land with a given accuracy again. So like I said, the classical example, a ball with a trajectory moving through space, something like this. We have starting velocity, a starting angle, a force of gravity acting on it. And we have some known equations that can tell us what the maximum height that ball will reach will be, or the greatest distance that ball will reach. These are things that will be limited by the precision of our initial measurements. If our starting measurements are plus or minus 50 centimeters or plus or minus a millimeter, our final prediction, the ball will land in that spot, will be plus or minus 50 centimeters or plus or minus a few millimeters. And the key thing is we can be as precise as we want to by making better measurements. If we want to know where the ball will land to within a few millimeters, we have to make initial measurements to within a few millimeters. That might mean using better equipment. It might mean taking more time. It might mean taking averages, all sorts like that. It might even mean waiting a few more decades for better microscopes to be invented to get that great level of precision. But the concept is the precision is continuous and we can always increase it somehow. Those are what we do with physics. A ball is a simple example. We do with fluids, we do with electricity, in greater applications, chemistry, biology. It's all the same kind of process. Quantum mechanics, when we get down to really, really small things, it changes it all up a bit. So we have the same 3 schema points that we want to implement, but with some limitations. Firstly, we cannot be as precise as we want to be. In classical physics, we come back with some better equipment or more time, we can be more precise. Quantum mechanics does not let us do that. We still have some equations and predictions that can give us future behavior, but we cannot get a specific answer based on our accuracy. So the first point, taking measurements, is limited by something we call Heisenberg's uncertainty principle, which sounds very impressive and complicated. It's summed up in this neat little equation where sigma x is how precisely we know an object's position. In this case, a quantum object, something smaller than an atom, like an electron or a photon. And sigma p is the uncertainty in that object's momentum. Those two things together sum up most of its physical properties. And this relation tells us that the product of these two has got to be greater than h over 4 pi. This is just a physical constant, 5 point something times 10 to the minus 34, just a number. So if we attempt to measure the position of an object, we'll become less certain of its momentum. Or if we try to measure an object's momentum, we'll become less certain of its position. And this is not something we get in classical physics. This is not something that happens to a football. A football, we can be more and more precise about its position, as well as being more and more precise about its speed, its velocity, and they don't interfere with each other. If we have an electron or a photon, we can have a rough idea. Its position is roughly here, its speed is roughly this much. As we begin to narrow one of them down, we get more and more precise. It's in this spot, it's in this very small spot. We get less certain about its speed, or it could be this much, or it could be this much. There's some range of it. And the other way around, if we start to get more and more precise observations of its speed, then we become less certain of where this object actually is. And this is a physical limitation on how small these things are. It is not something we can improve with better equipment or 10 years more technology. It's one of the quantum fundamentalities. That's one of the first obstacles we have to overcome. Predicting future behavior, we still have these general equations. This is the bit that's mostly the same. We put our starting date in the equations, we get an answer out. The difference is when we get to our future predictions. Firstly, they become probabilistic. So if we are observing a moving electron, we take its initial measurements, we use Schrodinger's equation to predict its movement. The best answer we could possibly hope for would be it's probably going to be here, it might be here, it probably won't be here. This is an accurate description, if not a precise one. Our equation might tell us it will land in this box 45% of the time, this box 20% of the time, this box 10% of the time. And then if we have 1,000 electrons going through the system, 450 will be in that box and 200 will be in that box. The equation is very good about ensembles of objects, but any single electron we start shooting down the system trying to predict where it will land, we won't be able to tell. The classic example is an electron or photon traveling through a single slit. We get diffraction, spreads out, kind of like a wave, though I don't want to talk about wave-particle duality. In a classical world, if we kicked a football towards a doorway, we would know where it was going to land. We take a measurement, how hard we kicked it, what direction. We know it's going to bounce off that wall and it'll break that vase in the hallway. We can be specific about that. If you have a quantum football kicked through a quantum doorway, or honestly just a very small doorway, quantum scale doorway, we can use the best equations we have and take the best measurements. We won't know exactly where it will land. If we do it lots and lots of times, we'll get some probabilities and some averages, but a specific one, we won't be able to predict its movement in the future. No matter what initial measurements or initial accuracy we have in a position or momentum, but not both at the same time. And these are essentially the weird differences quantum mechanics has that changes the way we have to deal with this physics and make predictions. So, jumping over to computing, firstly, we need to understand that a computer is just a physical system that goes through some predictable logical operations that we understand and can interpret some information from that. This model here is a little plastic toy from the 60s or 70s. It can be called a computer. These marbles move through it. These little white pivots are like gates. We know how they will behave. They pivot one way, something passes through, they pivot the other way. And when the marbles get to the end, we can interpret what that means in some way. It could be a red marble is a 1, a white marble is 0, and then 0, 1, 0, 0, 1. It could be number 9 in binary. It could be letter G in the alphabet. And then by rearranging these mechanical pivots, we could do different calculations. We could do addition or multiplication if marbles pass through, and then it loops some system until it's finished and get an answer at the end. Computers that we use day to day in your phone or PC are another kind of physical system doing the same thing, much more complex ways. We are using electricity and charged capacitors and transistors to act as these kind of gates. But those are all physical objects that we understand the properties of. If you charge one end of a transistor and another one, current will flow out here, and we know what will happen. In mathematics, we have something called a Turing machine, which is any system of these logical operations that together make up a whole computing system. The theory is really, really neat. You only need a couple of interacting things, gates or objects, to be able to compute basically anything, any numerical calculation, which can then encode any kind of information. It can become pixels and images on the screen. It can become 3D graphics. It can become sounds. Honestly, this plastic toy with a couple of adaptations could be a complete computer. If you just have the right little gates and then add enough of them together, you can get any kind of computation you want going on. What's the important bit? The important bit is computers are physical systems, which is why we use physics to build and understand them. In computation, like I was saying, you can do basically anything with a Turing complete computer. Some tasks are easier for computers than others. Factorization is the classic example of a difficult task. Computers are not good at it. Computers can add, computers can encode and decode information. Factorization, finding the factors of large numbers, takes a long time, even for computers, because they just run through all the possibilities, test them out until they get an answer. And as the numbers get bigger and bigger, the time that a computer takes to work out the factors of it, to factorize it, becomes unreasonably large, impossibly large, in fact, which is a key to a lot of computing security systems. So digital security is starting with some kind of information, encrypting it so that somebody that you don't want understanding it won't understand it, and then decrypting it back to something that can be read by someone that you want. This example has Alice and Bob sharing a key, which is part of the program to encrypt and decrypt things. They're called Alice and Bob because those use the letters A and B, and computer scientists have no imagination. In the rare case there's a third person in computer security examples, he is inevitably called Charlie. And encrypting, decrypting this information is done by a computer. It's fairly secure, but what do we mean by secure? In this case, it just means that it cannot be broken for a very long time. It's like if you ever to go to the gym and put a numerical padlock on your locker, you know that there's only 1,000 combinations on that padlock. If someone wanted to come along and test them all out, eventually they would break into your locker. But you know that would take them a few hours, by which time you'll be back, you'll be gone, the valuables will be gone. Computer security works in the same way. When a computer digitally encrypts something, we know how to decrypt it. well, you either use the key and decrypt it very quickly and easily, or you attempt to hack it and break it, work it out the long way around. All digital security used online now basically can be cracked by any computer with enough time. Why we still say it's secure is because it takes a very, very long time. Usually because it involves factorization of large numbers, which computers are not good at. It takes them a long time to do. Most cryptographic algorithms use numbers hundreds of digits long, and to factorize something like that, a computer would take millions of years, even the best supercomputer on the planet. And it's not exaggerating to say millions of years, because the mathematical theory has been worked out. So it's fine to use these theoretically crackable security systems on our computer, because by the time anyone cracked them, the Earth will have disintegrated. We don't worry about that. We can call it secure. But quantum computers could change that. That's why we are working on them. That's why some people are worried about them, and why we need more mathematical theories to understand what they are capable of. The idea of quantum computing started with Richard Feynman, an excellent physics lecturer, back in the 80s, suggested, hey, if computers are just physical systems and quantum mechanics is this new kind of physical system, could we come up with some new kinds of computers from it? In the same way they can have a charged capacitor or an uncharged capacitor representing a 0 or 1, that's the information you need to start working on a computer. Quantum objects can be in one of two states, upspin, downspin, horizontal, vertical polarization. You have the beginnings of something you can work on a computer. And then you need some repeatable, understood operations, rotate the spin of a photon, pass it through a polarization filter. You have the beginnings of those logic gates that make up computers. There was a lot of theory and ideas going on about this. In 1994-95, Peter Shaw came up with something that you can do on a quantum computer that you cannot do on a classical computer, which is factorize large numbers efficiently. This was really interesting, really exciting. The point was that these new quantum computers, if we could build them, can do things that classical computers never could before. Shaw's algorithm in particular, factorizing large numbers, suddenly had an application in digital security again, because digital security relies on those factorizations. If a quantum computer can do them quickly, they're not as secure as we once thought they were. RSA, Simon Chivest Adelman, is named after the three discoverers, is one of the most common digital security methods online. It relies on factorization, but using Shaw's algorithm on a quantum computer, we can't call it secure anymore. It can be calculated instead of millions of years, maybe a few hours. And that's enough to access your information online, access a bank database or anything like that. Suddenly that security parameter of taking a very, very long time to crack is no good for us anymore if your potential attacker has a quantum computer. What can we do about this? We start thinking of new kinds of cryptography that use quantum methods that classical methods could never use before. Some of those weird, quirky quantum mechanics things about being uncertain of measurements or having probabilistic instead of specific final predictions can suddenly be useful to us. This example on the screen is called quantum teleportation, which is a way of sending information from Alice to Bob without needing to do a kind of encryption that someone could potentially crack or break down. So then, instead of relying on our security being it takes a very, very long time to crack, but we know someone could crack it, The security is the physical laws of these objects prevent it being broken or attacked in any way. Because those uncertainties in the measurements, if you receive your photon from Alice and it's not as you expected it would be, you then know that someone has tried to attack it or tamper with it, because that uncertainty of your attacker measuring it must have changed the system. The uncertainty is something useful. It's a giveaway that your security has been compromised. Then you throw that out. You use a different method of communication. So the security of quantum cryptographic systems don't depend on time resources and being safe for millions of years. They physically cannot be cracked, cannot be attacked. Some places, Lloyd's Bank, I think is one, Cambridge University, have begun to set up quantum information systems using this that they know are perfectly secure. The problem right now with our technology is that it only works over maybe a few kilometers. There's 3 Cambridge University sites that can securely send information between each other, but it's still within the same city. This is not something that's going to change business, change our life, until we can send quantum information hundreds of kilometers across the country, across the world. And the limitation we get from that is what keeps us saying quantum computers in our everyday life are 10 years away, 15 years away. But honestly, physicists have been saying that for the last 30 years, maybe. It always seems to be 10 more years in the future. The key problem is signal degradation over long distances. If we use normal electricity down a telephone wire, over a long distance, it loses some quality, it loses some of the signal, some of the information doesn't come out right at the other end. But we have some mathematics that can reverse engineer it, that can fill in some gaps, that can correct errors, and we can use it reliably because we fix any problems that happen along the way. We build some better electrical wires with less degradation, and then we can have a worldwide internet. When we try and do the same things with quantum systems, quantum information wires, we get the same degradation. Over a distance, some of the information gets lost, the photon or the electron wave packet decoheres, it loses the bit that's containing information. But we don't really have any error correcting algorithms, anything that can make up for that loss in information right now. And because, like I was saying, the fundamental physics of these objects make them uncertain, have those little errors and difficulties in measurements ingrained in them, then it might not be possible in any way to build better wires. There are attempts to hold stable quantum states without decoherence for longer and longer times. Usually we need to use superconductors. It's expensive, and even long term for quantum information right now might mean hours. It doesn't mean long enough to transfer information. So the difficulty with these large-scale quantum systems for sending information is, firstly, we don't have the technology to do it without losing information. It might not be possible to make technology that doesn't lose information. And even if we do, we don't have the mathematics to reconstruct those errors or fix it up at the end. But we're still hopeful. We're still hopeful that quantum computers can be developed in the future that somehow fix these problems, or we can work our way around it, or we pair them up with classical computers. There's a bit of give and take to get these things that classical computers can never do. In addition to cracking old security systems, making better security systems in the future, quantum computers can do things better, faster, not possible null computers. Linear calculations, quantum computers are really, really good at, which get used in all sorts of things, from predicting weather patterns, protein folding. In biological sciences, amino acids are one of the fundamental building blocks of life, and they all fold up in strange ways. But the best supercomputers in the world can't work out how they do it, because, again, it takes millions of years to test all the ways they could arrange themselves. But if you have a quantum computer that can cut that down to hours or days, we have a much better understanding of biological science. If we want to simulate quantum systems, really we need a quantum computer. You can use a classical computer to model a ball bouncing, that's simple. When we're dealing with a few electrons, each with an up and down state, the computing cost of making a virtual version of that increases exponentially again. So if you want to model 10, 20, 100 electrons on a computer, the classical computer just isn't going to keep up. It won't be able to cope. Quantum computers are built for that. They're already using that kind of information. They can do these models in a way that be efficient and useful, and we can get something out of. Algorithms as well. Shor's algorithm is something you can only do on a quantum computer that factorizes large numbers quickly. There also is Grover's algorithm for searching. If you have a large database of unordered data, your classical computer struggles to go through it and search it efficiently. This new quantum algorithm, which makes use of these quantum properties, can do it quickly, can do it efficiently, in a way that a classical computer never could. And these are the kind of things that makes us hopeful that quantum computers will change the way we develop technology and what we can achieve computationally. Google was recently in the news saying they not quite achieved quantum supremacy, but had built a good, big quantum computer. But even then, it's the size of a laboratory. It still isn't the same scale as even 1980s Palm Pilot. The number of bits of information in it is still really small. But it's potentially happening. And in another 10, 15 years, or 10, 15 years after that, desktop quantum computers might be a thing. Or more reasonably, you'll have a regular computer on your desktop connecting to a quantum server somewhere that does the difficult calculation, then just sends you back the information that you want. My research in particular in this area is considering whether quantum computers really will be as good as we hope they will. I've sounded very positive about quantum computers tonight, and I do love the idea, but some of the physics behind it we're just not certain about. Some of the limitations that we hope we can overcome, like signal decoherence, depending on how you understand quantum mechanics, it might never be possible. If we can prove that it's never possible, no matter what we do, to get rid of that signal decoherence and be able to use quantum computers large scale, that would be important. That would change the direction of research. I'm not just trying to poo-poo on all of quantum computing research, but some quantum foundational ideas can really change how optimistic you can be about those kind of systems in general. These are a few choice papers on quantum mechanics and quantum computing. I've been a bit shorter on time than I expected, but like I said, this was all very experimental, and I haven't tried to do this talk before, and it is really weird not having an audience in front of me. But I think I've just about gotten through everything I planned to talk about. I hope there's some kind of understanding, or at least interesting, and if YouTube chat is still working. I can try and answer some questions if you like. Yeah. How was that? Is anyone... Is this chat still live? I now have to wait to see how long the delay in chat is before anything else happens. And again, I still have to keep talking, because if you just sit still on a webcam, it gets really weird and you don't want dead air. Yeah, shoot any questions you want into the chat and I'll answer what I can, as long as people are still viewing. Thank you all for being so wonderful and saying I did well. It was an interesting experience. I probably should try and get better at judging the length of my talks. Very interesting. Well done. Good. Thank you all so much. It's not quite the same as actually being in a cafe, being able to see you all and talk to you all and could mingle and ask questions casually. But this is what quarantine science is going to be like. This probably won't be the last live streamed Cafe Science talk, I expect. I'll be happy to come back and do it again if anyone likes. Questions. Is there no possibility of signal boosting as in conventional communication systems as required reading the data middle? Yeah. Quantum relays that can boost signal like we do classical information does essentially break down everything useful about sending information in a quantum way. When we encode some information in a photon or electron, it's wave packet something, we are using the fact that reading it destroys the potential information, giving you just what you want. And relays or signal boosters have to do that. They have to read it and then send it on again somewhere, in which case they're not really a middleman, they're an endpoint. A classical signal you can send from, where's the edge of the camera, Alice to Bob, and somewhere in the middle you just boost what's already there so that it gets to the other end. If you have a quantum system, your middleman, your boost, would essentially just be a receiver. They would have to receive it, understand it as classical information, and then send it on again to Bob. So you haven't actually extended the range that you can send information. You're just doing it in shorter packets, in which case you have to trust every receiver along the way with your information. I hope that makes a kind of sense. Is it possible to judge if the cost of quantum computers will be in the same ballpark cost-wise as current ones? In terms of like consumer costs, will a desktop quantum computer ever cost the same as a desktop PC right now? Possibly. It's Moore's law again. The relationship between transistors in a circuit board is also a link to the price. So a computer as powerful as this one in a couple of years will be about half the cost. If that trend continues to quantum computer systems, then they will be at an affordable price, possibly for consumers. That's still decades away right now, because right now the best quantum computers exist in labs with specialist equipment. If they ever became a commercial thing, they would obviously be at a commercial price, if that's what you mean about cost-wise. I mentioned the weather. What other examples might a quantum computer predict? Weather systems, chaotic systems are one of those things where it just takes a lot of input information and then a whole load of linear calculations to get some kind of prediction at the end. Those are the kind of things quantum computers are good at. So fluid dynamics can be improved. Right now we have averages of fluid systems. If we can do calculations, smaller parts of it accurately and reliably, uh, it's like trying to measure a sandstorm. It's technically classical mechanics. Each grain of sand is just a particle moving according to normal physics, but there's so many of them, it becomes infeasible to compute. A quantum computer doing lots of linear calculations effectively at the same time makes that more practical again. Quantum computers, whether, given the security implications of such a disruptive technology, how cooperative is international academia right now? International academia is, I don't know, as good as it's always been. Academics, mathematicians, physicists studying things generally study it for the sake of studying and share the information to their journals, online sources. It's not like a nuclear arms race where we're worried about one country developing it before anyone else and then being able to hack all the world's security systems. Any development towards workable quantum computers that could be major security risks happens in very small steps over lots of papers, lots of journals, lots of people. Honestly, if the first working quantum computers will come from Google or IBM or some big corporation that will be publicizing it. It's not being developed clandestinely by the CIA. Well, maybe I'm pretty sure the CIA is doing computer research, but I don't feel like there's a major risk of a single user having a quantum computer and breaking everything, because it is still a long way off, and everything to come together to build that will go through public knowledge, peer review, academic circles, shared around the world between researchers and people reading these journals before it gets to that. Saying that, I might actually mention where was it? The RSA algorithm. I said it was developed by those three in I can't remember the year now. 80s. They developed it and published in a journal. No, I'm misremembering. Sorry, it's not RSA. It's BB84. BB84 is a quantum security protocol published in 1984 by academics in a public journal. Everyone read about it. It was cool. It turned out GCHQ, the UK intelligence division, had effectively developed it a few years earlier in an internal memo that they didn't share. That was an example of, like, say, one of these independent developers getting ahead of the game. Something they knew about it, but didn't tell anyone else and had an advantage. Luckily, it didn't change everything, and it wasn't too long before it was released publicly. It was developed independently. But yeah, just an anecdote. Like weather implications. Is the degradation gradual? As in, is there any range at which packets could be recovered if the range is short? Yeah, sort of. Like I was saying, over a few kilometers, we can send quantum signals. That has improved over the last few years, few decades, from sending signals from one end of a lab to another. And the information we lose is related to the probabilistic measurements. If it's a very long distance, it ends up unlikely you will have that kind of linked information that you want. Over short distance, it is likely. And yet there is some point at which you have to decide we are losing reliability in the information and have to say we basically can't send information past that distance, and distance is shorter than that. We say we pick it up often enough to recover what we want. Orion 209, I think that was about what you were meaning. Are there any more questions popping up? I'll hang about a bit longer in case anyone's still there, still interested. But yeah, I hope this has been interesting. It certainly interests me enough to research it at least. I suppose I might do a follow-up talk some point, getting more into the technicalities of how quantum encoding, quantum information system can work. If Science Cafe will have me or wants another speaker on a similar topic. I try to keep it quite light and easy and and explain using analogies rather than equations of physics right now, because I honestly wasn't sure what quite level to pitch this talk at. The questions have been really good. You are an informed audience that we managed to keep up at least. So yeah, maybe I could be a bit more technical, a bit fancier next time. Thank you all for the messages of thanks and being so nice. I believe this video will stay on the Science Cafe YouTube channel if anyone wants to watch it back or share it with your friends or delete it forever because it's horrible. I don't think it's been horrible. Definitely rambly. I didn't set out a fixed script, I didn't have a good time, but it's been interesting. I'm still getting used to live streaming talks instead of being in front of people. Yes, thank you, Ozzy. See everybody again on the 27th of April for the Biomechanics of Dinosaurs with Kat Strickson. Excellent, sounds good. I will be there. And I hope everyone else will be too. Hope everyone else stays well during quarantine and lockdown. And that we all manage to get through it. Yes, I'll be happy to be back. Sounds brilliant. Yeah, so 1749. I guess I'll call this to a close in just a minute at maybe 10 to. If that's enough questions for now. I guess if there's any further questions at any point, message Science Cafe YouTube channel or you can maybe pass that on to me. I can try and respond. Yeah, so if this is about everything, then I'll say goodbye, and Rosie can stop the stream whenever we're done. I'll sit here awkwardly until it looks like it stopped. Honestly, it's a whole complicated thing, but I think we managed it. It worked out pretty well. Technology was not as awful as it could have been. Good night. Good night.